Okay, start from the beginning. You're good.
Welcome to my presentation called Scaling Stuff in the Summer. I'm going to be quickly presenting 3 projects. One is called Jumbo for compute-efficient plane vision transformers, LookWhere for adaptive computation via distillation, and self-souping more models, no labels. So I'm a 3rd-year PhD student at Carleton University, supervised by Jim Green. I'm most interested in computer vision, self-supervision, transformers, and many applications. Most importantly, I'm just finishing my vector research intern with Evan Shellhammer, who's a faculty member at UBC and Vector. And I will very quickly, so sorry in advance, cover 3 projects, Jumbo, LookWhere, and self-souping. So fast vision transformers with a Jumbo CLS token. So some background on vision transformers. So again, transformers receive a set of tokens as the inputs. So in language models, which everybody here has used, the tokens are words or subwords, like a couple letters or a full word in your vocabulary. And in vision transformers, tokens are image patches. So these are non-overlapping regions, little squares, as you can see down here in this image, that are essentially the tokens in vision transformers. And so crucially, we append a classification or CLS token to the sequence of patch tokens, and that classification token gets processed by the transformer encoder with all the other tokens, and then you use that to classify the input, saying it's a dog or a cat or whatever your task is. And so visually over here, we have this image, we're patchifying it into these patches. So we have these sequence of tokens, we add position embeddings, the CLS token here on the left, and then we send it through just a vanilla transformer. Okay, so we introduced Jumbo. So Jumbo is very simple, but also highly effective. So it's essentially just an extra wide CLS token that affords much more capacity, but is very cheap because it's just a single token. And so Jumbo has a much larger single feed-forward network or multi-layer perceptron. This is the second sub-layer in the sub-figure to the right. I think you can see my mouse. So this is MLP. It's the same thing as an FFN. And this is very large, so it has a lot of parameters, but we share the parameters across the layers to control the memory, and this is highly effective. So Jumbo is a plane vision transformer, which means it's attention only and non-hierarchical. Thus, Jumbo can support token dropping for efficiency or self-supervision, other domains like time series or 3D point clouds, and it hooks up into the ViT ecosystem, for example, with segmentation heads or test time adaptation methods. So crucially, Jumbo remains a plane vision transformer while achieving state-of-the-art compute efficiency, where compute efficiency is basically the speed accuracy trade-off. So for experiments, we mainly care about the speed accuracy trade-off and plane ViT compatibility. So plane ViT compatibility is attention only and non-hierarchical, which have these nice features. They basically make things simple and make them all extremely flexible. And so we're going to compare against state-of-the-art models in compute efficiency and plane vision transformers. So on these plots, on the x-axis, we have throughput, which is images per second, so speed on the x-axis. On the y-axis, we have accuracy, so you want to be in the top right of these plots. And so our model Jumbo outperforms the state-of-the-art against compute-efficient architectures, which is a big deal, but it retains the plane ViT advantages. Okay, so next project is called LookWhere, so efficient high-resolution visual recognition. So our goal is, instead of processing all the regions of a high-resolution image, which would be extremely expensive, we're going to quickly select the interesting regions and only process them, right? And if you're only going to process the interesting regions of a high-resolution image, then it's going to be much cheaper, because if that's like, 5%, then you're only computing 5% of the locations on the image. So our plan is to use a self-supervised teacher, for example, Dino V2 or Dino V3 or Franca, for attention maps of where to look or like where to process in the image, and then representations, which are what is actually in the image. So like this is a bird, this is the type of bird, and where the bird is in the image, within the image. And so we're going to do this via pre-training via distillation. So we're going to train a selector to predict the teacher's last layer attention maps. So the selector is basically trained to kind of predict where to zoom into or decide where to zoom into, essentially. And then we're going to train an extractor to predict the teacher's representations, and the extractor only gets the sparse subset of patches that are deemed interesting by the selector. And the selector is very small and it just receives a low resolution version of the image. So that is very lightweight and fast. And the extractor is also lightweight and fast because it just receives a sparse subset of patches. And both targets are computed with a single forward pass from the teacher, so pre-training is also efficient. During fine-tuning, for like deployment or downstream usage, we will discard the teacher, and then we're only going to update the extractor, and this is highly efficient for fine-tuning. And shout out to my nephew Braden, who this is him in the picture. Okay. Also, this is my niece Sophia's eye. Sorry, just like that. Okay, so for experiments, yeah, LookWhere outperforms the state of the art for adaptive computation methods. And this is maybe a more interesting example that I like. So the task here is to, I don't know if you can see this, but the task is to predict the speed limit right here, and it's 70. I'm not sure if you can see it at the back, but the speed limit is 70. And that's really the only part of the image that you need to successfully complete the task. And so we're going to downsample this image, give it to the selector. The selector outputs this map, which is essentially like where to compute or where to zoom into. It's going to say, okay, some parts of the road, the sign right here, those are interesting, but like the background, the trees aren't really that interesting. So don't worry about that. And then so these patches are selected, and we give these patches to the extractor, which then makes the prediction. And so our model LookWhere performs just as well as DynaV2, which receives the full input, but it's way, way faster. Okay, so the final project is called self-supervision. So cooking model soups without labels. So some background on model soups. So the recipe is, first we pick a pre-trained model, like DynaV2 or even in language GPT-2, whatever. We're gonna and so this pre-trained model is this red model over here on the left. We're going to fine tune it n different times. In this case, n is 3. So we're going to fine tune it to create a blue, a yellow, and a pink model over here. We're then going to average the weights to create this multicolored model down here. And we're going to deploy it. And when we deploy it, it's just a single model. So it costs just as much as any model, but it's going to be more accurate as long as the soup was cooked correctly. And so our goal is to create model soups without labels, just with self-supervised learning. And so our recipe is to pick a pre-trained model, independently intertune, or train it n times using self-supervised learning. And so self-supervised learning is training models without labels or annotations with some like pretext task kind of thing. And then 3, we're optionally going to fine tune it on our target task if we have one, like ImageNet, but we don't have to do that. And then 4 is we're going to average the n set of weights, and again, we're going to deploy it. And so preliminary results, basically the blue ingredient, which is a model over here, we intertuned that with a reconstructive pretext task. So like hide the patches and predict the hidden patches kind of thing. And then the orange ingredient we trained with a contrastive learning objective, which pulls together representations of the same sample and pushes away other samples. And if we average the weights just in a 50-50 mix, we get higher accuracy than either of them separately, and especially out of distribution where we see this like 2% gain. In distribution, it's not as much, but it's still nice. And so of course, the soup is more accurate than its ingredients. And we can also scale this up to 24 ingredients, in which case we show that self-souping is better on ImageNet. So this is like in distribution, and then also out of distribution, it's also better. So next, we're going to transfer beyond ImageNet. I'm just looking at the time. Okay, so transfer beyond ImageNet. We're going to mix more ingredients and some using KNN, and then potentially self-soup in space. And that's it. Thank you.
Questions? Judges, questions?
Yes.
So I went on the LookWhere components. Back just to talk about it. So in the actual sparsification where you are thresholding I guess the attention maps here, how do you choose how much to keep?
Yeah, so that's a user decision.
Okay, so that'll be a hyperparameter that you
Yeah.
guys are doing. Did you find that there was often like a particular threshold after which you really lost accuracy? Like, what was the trade-off?
It really depends on the task.
Okay.
Yeah. So like ImageNet, you can get away with very few patches. Also because the selector, because like ImageNet, you can also do well with low resolution images. And so like the selector actually didn't, I skipped this because it was maybe a bit too much detail, but the selector also gives the CLS token, its CLS token to the extractor. And so if it can do a good job on the low res image, then the selector like does a good job. And so it just needs a few high res patches. So an ImageNet's fine. But on stuff like traffic, then you definitely need like at least 10% of the patches to kind of isolate this. It also depends on how good your selector is, right? Because if like for example, if we had a worse teacher that was going to train the selector to like zoom in over here, then we need a higher K to capture the traffic sign, which is in our task.
Just as like an immediate follow-up that occurred to me, I think these are ImageNet, but I'm curious if there was something like a multi-class classification, like a multi-label classification problem where you had, for example, like multiple classification tasks that you were trying to do. Did you guys think about or test on any of those? 'Cause I'm curious, because you're gonna get the competing attention and how you select patches is going to be a little bit more.
Yeah, so the selector is trained just from Dino V2, so with the self-supervised model. So and we actually don't fine tune the selector during when we fine tune the extractor. So the selector is always general.
Okay,
It's just the extractor we have to specialize.
yeah, but I do imagine if you had multiple objectives, you might be starting to spread attention out, right? Like it becomes more uniform because there's more areas probably that matter.
Yeah. There actually is, I don't have it here, but there's this billiards ball data set, which is a synthetic data set with billiards balls, and you have to zoom in to find the numbers. And so, but you have to like find the bigger number among the leftmost and the rightmost ball.
Okay.
So you have to zoom in into multiple portions.
Yeah.
Yeah, this is in the appendix of the paper.
Yeah, that's a good example.
Yes.
Can you just highlight the benefit of each of the projects in like a one sentence?
Okay, so with Jumbo, it basically makes plain vision transformers fast. Beforehand, plain ViTs were like really bad on ImageNet, so like 60%, which is considered quite bad, but we're like in the mid-70s for the same speed. For LookWhere, I think it makes high resolution computer vision more accessible. And then for self-souping, let's see here. I mean, a lot of applications don't have labels, and so if you want to make a soup, then you should turn to self-souping. Okay, thank you.